In this video, we solve homework problem 13.4.033 from the Larson and Edwards Calculus Early Transcendental Functions textbook, 7th edition. It's an application problem, and it involves the differential. Oops, there's a letter missing there. It says, the inductance L in microhenries of a straight non-magnetic wire in free space is given by this equation. L equals 0.00021 times natural log of the quantity 2h over r minus 0.75, where h is the length of the wire in millimeters. We've got some wire like this, and this length is h. And r is the radius of a circular cross-section. So it's a little bit hard to draw, but it's the radius of that little circle over there. That's r. It says, approximate the length when r equals 2 plus or minus 1 over 32 millimeters, and h equals 100 plus or minus 1 over 70 millimeters. And then you're asked to round your answer, to 6 decimal places. So the way we want to read these is this is the measured value of r, but we could be off by a little bit. Anytime we take a measurement, there's always some error involved. And this is our approximate error. We're saying r could be off by plus or minus 1 over 32 millimeters, or something less than that. But that's the maximum that r could be off. And we tend to think of this as maybe the measured value of r, so you could call that r naught if you wanted to, plus or minus dr. I know that dr might be a problem for some of you, but just think of it as a tiny change in r, or the error in measuring r. So approximate the length when r is equal to this and h is equal to this. In the same way, we can think of this as the measured value of h, and we might be off by plus or minus 1 over 70 millimeters. So we can think of that as dh. And so when they ask us to approximate the length, what they're really asking us for is L equals what? They're saying L equals L naught, that's the measured value of L, or actually the calculated value of L, using this value of R and this value of H, plus or minus DL, where DL is given by our differential formula. And this is going to be the maximum DL. This is the maximum error in measuring L. So remember, I guess we should probably use absolute values around all of these. Remember from our lecture over differentials that whenever we're talking about propagated error like this, the measured value or the propagated error in calculating L can be found this way. If L depends on 2 variables, and it does, look at this equation. L is a function of both h, that's the length of the wire, and r, that's the radius of a cross-section. So L is a function of 2 variables, so the differential is going to have 2 terms. Typically, if I was just doing the differential, I would have the partial of L with respect to h times dh plus the partial of L with respect to r times dr. But we're talking about error. So we want to put absolute values around all of these guys, because it really doesn't matter what the signs are here. Well, actually the signs do matter, but when you're calculating the error, the signs don't matter. Both of those could be negative, and then that would be the error, and that would contribute to error over here. Okay. So this is our inequality that we're going to use to calculate this DL. This is the maximum error in measuring L. And then we want to use just this formula here to calculate L naught. So let's do the easy part first. L naught is the value of L that we get when we substitute h equals 100 and r equals 2. So it's just L equals, or L naught equals L of h naught r naught. And we have 2h over r in the parentheses there. And h naught was given to us, that was 100, that's the measured value of h. And r naught was 2, that's the measured value of r. This is 2 times h, which is 100, over r, which is 2. So we get that. Obviously the 2's reduce. And so we've got natural log of 100 minus 0.75 times that. And we want a decimal. We're asked to round to 6 decimal places. Sorry about that reflection there. So I've got, I'll do what's in the parentheses first, natural log of 100 minus 0.75. You want to take that and multiply by 0.00021. And we get that. So that's approximately 8.0955857 times 10 to the negative 4. And remember what scientific notation means. That means you just want to move that decimal out 4 units this way, or 4 places that way. So you're going to have 0.00080955857, and we only want 6 decimal places. So I want to take that and round. Oops. And we'll round up. So we have 0.000810, or if you prefer, you can use the scientific notation, 8.10 times 10 to the negative 4. That's the same thing. Okay, so that's our L naught. And now we just need to calculate DL, and that requires computing the partial of L with respect to H and the partial of L with respect to R. And remember, both of these are evaluated at that base point. So we want to evaluate this partial derivative at, because I'm using H as my first variable, H naught, R naught. We want to evaluate this at H naught, R naught as well. So let's compute some partials and then we'll plug in those points. Partial of L with respect to H is the partial with respect to H of this quantity, 0.00021. And then we have natural log of 2H over R minus 0.75. Now you actually have some options here. If you want, you can use the chain rule for this, but this is actually much simpler if you use some algebraic identities for logarithms. We've got some log properties that will allow us to simplify this. So here are the log properties that I would use just to make the differentiation easier. If you just take the derivative using the chain rule, you're going to get the same answer. Remember that log of a quotient is log of the numerator minus log of the denominator. And log of a product is log of the first factor plus log of the second factor. With both of those identities, even before I take the partial derivative, I can rewrite this way. Natural log of the quotient is natural log of the numerator minus natural log of the denominator. And natural log of 2 times h is natural log of the first factor plus natural log of the second factor. And all of that is in parentheses and here. So that's going to make this really easy when we compute the partial with respect to h. And when we compute the partial with respect to r. So we've got all this. That's a constant times a function of h. So you want to bring your constant down. And the derivative of natural log of 2 with respect to h is 0. The derivative of natural log of h with respect to h is 1 over h. So we're taking this guy and we're multiplying by 1 over h. It's the same as dividing by h. There's no h here, so the derivative of that with respect to h, treating r as a constant, is 0, and the derivative of that is, of course, 0. So this is the partial, This is the partial of L with respect to H, and we want to evaluate this at H naught, R naught. So I guess we can write it this way. I'll use subscript notation now. H naught is 100, R naught was 2. So we've got 0.00021 divided by 100. That's going to be 0.0000021. You're just moving that decimal over twice. Okay, so that is the partial of L with respect to H at H naught, R naught. So that's going to go right here. We're going to do the same thing with respect to R now. And I'm still going to use that form of the function that we got after simplifying using our log properties. Okay, I've got a constant times a function of R, so we bring down the constant. This doesn't have an R in it, so the derivative is 0. That doesn't have an R in it, so its derivative is 0. Then I've got a -1, so I bring that down, times the derivative of natural log of R with respect to R, which is 1 over R, or you can just divide by R, that's the same thing when you multiply all those guys together, and of course the derivative of the -0.75 is 0. So that is the partial of L with respect to R. We want to evaluate that at 102. So I've got -0.00021 divided by 2. So we're going to get -0.0000105. Okay, so that's going to go into our formula for DL. And remember what this is. This is the maximum error in calculating L using propagated error formula. So if H is measured to be H naught and R is measured to be R naught, and H is off by potentially this much and R is off by potentially this much, the maximum error in measuring L is this number over here. So we're just going to put all of our pieces together. Having trouble today, having trouble talking. Okay, it happens, right? Got to give ourselves some grace. Give each other grace. Okay, at this point, or at this step, I'm just substituting this in right here. And I multiply by DH. Now remember what DH was? That was given to us. That was that 1 over 70 millimeters. And actually, we should probably mention units. So let's look at these partial derivatives again. I have this number. If I'm asking myself, what is that number? What are the units for that number? It's going to be units of the numerator over units of the denominator. Because remember, with partial derivatives, you're treating the other variables as constant, and you're basically looking at the instantaneous rate of change of this quantity as this quantity changes. This quantity is being measured in microhenries. And I actually don't remember the abbreviation from physics. So I'm going to write it out like that. That's the same way that they write it out in the WebAssign website for our class. This is microhenries per unit change in H, and H was measured in millimeters. So this is microhenries per millimeter. So that's the instantaneous change in inductance as this length of our wire increases by 1 millimeter when the measured length of the wire is 100 millimeters and the measured radius of the wire is 2 millimeters. So those are our units here. So we've got microhenries. That probably shouldn't be there. Microhenries per millimeter. And of course, when we multiply these guys together, the millimeters reduce and we just end up with some number of microhenries. Now this would be it. If we were absolutely sure of the radius of that wire, but we thought the length of the wire might be off, this would be the maximum error in measuring the inductance, but it's not. We're assuming that H could be off by a little bit and R could be off by a little bit. So this is the change in the inductance that we would expect due to a change in the length of the wire by 1/70 millimeters. It's the error that we would expect. Similarly, this is a number of microhenries per millimeter. And we need absolute value bars around that. Because this could be off and this could be off in the same direction, like this could be negative and this could be negative. If that's the case, when you multiply them together, you're still gonna get contribution to the error in measuring this. So we need absolute value bars here. And dr that was given to us, that was 1/32 millimeters. And when we multiply those together, our millimeters just reduce, and we just get this times this number plus the absolute value of this number times that number. And then we want to round to 6 decimal places. And I get that. That is 3.28425 times 10 to the negative 6. Now, if I were to write this, not in scientific notation, but just in our standard notation, I would move that decimal over 6 times. Okay, that's approximate, but they said to round to 6 decimal places. So that's the answer. That is our maximum error in measuring or in calculating inductance using this number of millimeters of length, this radius, given that we have some error in measuring the length and some error in measuring the radius. So they asked you for L naught plus or minus DL. Oops. And you kind of don't need the absolute value bars here. People typically know that that's going to be positive whenever you're using this notation. But that's probably a good reminder whenever you're doing propagated error problems. Maybe in calculus class you want to write it this way because that should always be positive. We don't want to have a negative number here times plus or minus. The maximum error is going to be a positive number. Okay, so our L naught, that was something we calculated earlier. That was this, or you could write it as 8.10 times 10 to the negative 4. Plus or minus this. And if you prefer, you could write that as 3.0 times 10 to the negative 6. And of course, the units for that are microhenries.